from chapter 6. This is question 16. So in question 16, what we are looking at is a problem where it's asking for what the frequency is once we've been given a wavelength. So part A tells us that we have a wavelength of 10.0 angstroms. Now an angstrom is a very small unit. The conversion factor for angstroms is actually located in your textbook, and it says that an angstrom is 10 to the negative 10th. That's what an angstrom is. So if we're dealing with meters, and we have our formula, which is nu lambda equals the speed of light. So it's the wavelength times it's frequency times the wavelength equals the speed of light. And what I'm trying to do is I'm trying to solve for, we're given the wavelength, but the question's asking for what's the frequency. So we're going to need to take lambda to the other side. So nu is equal to the speed of light divided by the wavelength. And that'll tell us our frequency for our part A. So when we're trying to figure that out, we have to know what C is. C for all of our problems is going to be 3 times 10 to the 8th meters per second. That means if we're going to be working with this angstrom here, this is actually the given, the 10.0 angstroms, we need to convert the angstroms into meters. So it's 10.0 angstroms times our conversion factor, and we're taking it to meters. So meters on top, angstroms on bottom, and the conversion factor is for every angstrom you have 1 times 10 to the negative 10th meters. Alright, so you do the math, and then you end up, get out my calculator. So the math on this one is 10 times 1e negative 10, enter, and then I end up with 1 times 10 to the negative 9th meters. So that's my lambda. So now I can plug in my lambda here in my equation and then take my speed of light and plug it in up top. So frequency is equal to 3.0 times 10 to the 8th meters per second divided by 1 times 10 to the negative 9th meters. So what will happen when I do this math is I'll have 3e 8 divided by 1e negative 9, and I end up with an answer which is 3 times 10 to the 17th inverse seconds. See, the meters cancels out and the seconds is still in the denominator spot, so we write it down as an inverse second. Alright, so I've got my answer for A. Now for question B on number 16, it says what wavelength of radiation that has a frequency, or what is the wavelength of radiation that has a particular frequency of, and they give you the frequency. So when we do B, on B, you're still dealing with the same equation, which is that the speed of light is equal to nu lambda, which is, frequency times wavelength. That's what it always is. And then they give you a frequency. They tell you the frequency in inverse seconds, which is 7.6 times 10 to the 10th inverse seconds. Alright, now I have to solve for wavelength, so I'm going to have to rearrange this equation up top. So I got to get wavelength by itself. Frequency goes to the other side. So lambda equals the speed of light divided by the frequency. Don't forget that the speed of light is always 3.0 times 10 to the 8th meters per second. I believe that's on your formula sheet. Then you just have to plug these two numbers in. So the lambda is equal to 3.0 times 10 to the 8th meters per second divided by frequency, 7.6 times 10 to the 10th. And that will tell you your wavelength. So in my calculator, I just type in 3e8 divided by 7.6 e10. You end up with an answer of 0.0039 meters. And that's your wavelength. Now we have to talk about, let's see here, that's B on question 16. Now C, it says, what would the radiation in A be detected by, or part B, which one would be detected by X-ray? So if we look at this one, we look at the wavelength that we're dealing with, and we go back to A, So A, the wavelength we'd be dealing with, could actually be X-rays, and that's our wavelength is right here. For B, our wavelength is closer to microwaves. So A is X-rays, B is microwaves. Now we have to do D. Now D asks what distance does the electromagnetic radiation travel in 25.5 femtoseconds. So D tells us that we have radiation traveling for a period of time which is 25.5 femtoseconds. Alright, well, this is sort of speed equals distance divided by, distance divided by time. Don't forget that our speed is always going to be in meters per second. That's how fast something travels. That should be back from your physical science days. So since it's meters per second, and we know that the speed of light is traveling in 3.0 times 10 to the 8th meters per second, if we take that speed of light and multiply it by some value of seconds, it's going to tell us how far we travel in meters. There is a formula for it, which is rate equals distance over time, but I don't need to write that down because you probably remember it from 9th grade. Now what we're going to do is we just have to get femtoseconds into seconds. So a femtosecond is times 10 to the negative 15, so it's 25.5 femtoseconds. Times, we're taking it to seconds, femtoseconds on bottom, it's 1 times 10 to the negative 15. We end up with an answer that's 2.5 times 10 to the negative 14th seconds, and that answer right there goes in there. You multiply the two, and you end up with a distance of 7.5 times 10 to the negative 6 meters. If you have any other questions, please let me know.